ಹಲೋ ಹಲೋ, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ಸರ್? ಓಕೆ ಸರ್, ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್. ನೀವೊಂದ್ಸರಿ ಮಾತಾಡ್ತೀರಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಡಾಕ್ಟರ್?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್, ಕೇಳಿಸ್ತಾ ಇದೆ. ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಇಲ್ಲೇ ಕಾಣಿಸುತ್ತೆ ಸರ್, ಡೈರೆಕ್ಟ್ ಆಗಿ ನಿಮಗೆ. ಸರಿ, ಅಲ್ಲೊಂದು ಚೆಕ್ ಮಾಡ್ತಾರೆ ಹುಡುಗರು.
ನಮಸ್ಕಾರ ಸರ್. ಪ್ರೊಫೆಸರ್ ಹಲ್ಗೇರಿ ಸರ್, ನಮಸ್ಕಾರ.
ನಮಸ್ಕಾರ, ಗುಡ್ ಮಾರ್ನಿಂಗ್.
ಹೇಗಿದ್ದೀರಾ ಸರ್? ಸರ್, ನಮ್ಮ ಚೇರ್ಮನ್ ಪ್ರೊಫೆಸರ್ ಅಯ್ಯಪ್ಪನ್ ಸರ್.
ಹೌದು, ಓಕೆ. ನಮಸ್ಕಾರ ಸರ್. ನಮಸ್ಕಾರ, ಗುಡ್ ಮಾರ್ನಿಂಗ್. ಗುಡ್ ಮಾರ್ನಿಂಗ್. They are not that we are executive of this idea. Earlier, you was there. Now,
Dr. Anand sir, thanks for joining.
okay. Good morning, sir.
Thank you for joining this webinar, sir.
Okay. Unmute ಮಾಡಿದೆ.
Dr. Lokesh.
ಸರ್,
ಮೇಡಮ್ ಬಂದ್ರಾ?
ಬರ್ತಾ ಇದ್ದಾರೆ ಸರ್, ಬಂದ್ರು.
ಈ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲಿ which is better? This web has now a lot of.
Ramesh sir.
Good morning, madam.
Good morning, sir. Good morning.
Thanks for joining this webinar.
It is my pleasure.
Very kind of you. Chairman sir, shall we start? Start, Ananda? Yeah. Good morning. Good morning, everybody who has joined for this international webinar. At the outset, I welcome you all for this webinar. Our Honorable Chairman, Professor Ayyappan, has joined for inaugural session. On behalf of all of you, I welcome you, sir. Eminent chemistry scientist, Dr. Rolgariser, sir, Director of Pune Institute of Scientific Research, has joined with us. Sir, on behalf of all of us, welcome to you, sir. Honorable Registrar of VSKU University, Professor Tulsi Mala Madam, has kindly joined this inaugural session. On behalf of all of us, hearty welcome to you this inaugural session, Madam. My good friend Dr. KSTA&T, Professor and Chairman of Chemistry Department, has been very kind enough in joining with us in organizing this program. On behalf of all of you, welcome, Doctor. And before beginning, I must mention here that there are 250 registrations so far. Now they have 75 participants have joined. Most probably in another half an hour, another 200 may be joining. Well, with this, let me briefly tell about Academy. Karnataka Science and Technology Academy was started in the year 2005 under the chairmanship of renowned space scientist and former chairman of ISRO, Professor U.R. Rao. Now, KSTA is chaired by distinguished agriculture scientist and former DG of ICR and secretary where Professor S. Ayyappan is guiding us since 7-8 months. KSTA has covered entire educational pyramid, right from high school level to the university level, catering to the requirement of students studying at various levels. In fact, we regularly used to organize PG special workshops in association with various universities across the state every year. But this year, due to COVID, we have not been able to organize rather physically. Offline, we have been organizing regularly. For this particular webinar, we have associated with VSK University, Honorable Vice Chancellor and Honorable Registrar have kindly agreed to associate with us. On behalf of all of you, thank them. And I must mention here that my good friend Dr. Lokesh has been very kind enough in identifying resource experts for this particular webinar. We have 8 sessions in this Advances in Chemical Sciences. which will be organized for 4 years, 4 days from 19th to 22nd January. We have two keynote addresses and 6 distinguished talks. Today we will be having talks by Dr. Anand Rolgariser, Director, Purna Pragna Institute of Scientific Research. His keynote address will be on sustainable waste to chemical processes, chemical fixation of carbon dioxide by capture and conversion into fuels, and chemicals by porous catalysts. And the second keynote address will be by Prakash P. Vadgaonkar, who was the chief scientist of in CSIR NCL lab Pune. He'll be speaking on sustainable chemicals based on byproducts of agro-processing industries. Followed by that, we have 6 distinguished talks by eminent speakers from national research labs and also one from industry. Professor Shashidhar is a senior scientist in CSIR NIIS Trivandrum. He will be speaking on natural products in drug discovery, past, present, and future perspectives. Followed by that, tomorrow afternoon, second talk will be by Taramani CN. She is an assistant professor at IIT Ropara. Then third day, we have another 2 talks first by Dr. Sharmishta Dutt Chowdhury, senior scientist, Park Mumbai. She will be talking on UV and fluorescence spectroscopy, basic principles and so on. And the second talk will be by Dr. Subramanya, senior scientist in Sinjan, Bangalore. And fourth day will be by international speakers. First by Dr. M.V. Reddy, he is a senior researcher in the Institute of Research, Hydro-Quebec, Canada. He will be speaking on materials chemistry and applications and research opportunities. And the second talk will be by Dr. Nagaraj Basvegowda, who is the international research professor at UNAM University, South Korea. We'll be talking on metal and metal oxide nanocomposites for catalysis, biomedical and other applications. So these 4 days we will have very good talks by eminent speakers. I urge all the student participants who are present here to be attentive for 4 days. You will get a lot of information on advances in chemical field and also opportunities for research. And this will, I am sure, will be helpful in your career progression in the near future. With this, I once again welcome all of you, and now I request Professor Tulsi Mala Madam, Registrar of VSK University, for her brief talk on this particular occasion. Over to you, Madam.
Thank you, sir. Good morning to you all. Respected President, officers of Karnataka Science and Technology Academy, Professor Shivprasad sir, Professor Lokesh, and dear delegates. At the very outset, I would like to congratulate KSTA and also Department of Studies in Chemistry of our university for organizing this international webinar. Really, I am privileged to be a part of this wonderful academic endeavor. It is a very well-known fact that chemical sciences, they are playing an increasingly important role in our day-to-day life, society, and also economy. In the current scenario, chemical sciences, they have proven that they have sufficient potential to address the major challenges related to energy management, environment, climate change, health, water, food production, and so on. As a result, now across the world, there is a growing demand for chemical sciences. Further, the ongoing socio-economic changes, technological changes, and also changes in the paradigm of development as well as governance, they are producing sufficient implications for changing the nature, orientation, and also scope of chemical sciences. As a result, chemical sciences, they are becoming more interdisciplinary, and they are also becoming more problem solving than purist. In fact, the changing contours of chemical sciences and their role, and also the impact in a rapidly changing society, they are driving the recent advances in chemical sciences. So we are hopeful that the recent advances in chemical sciences, they go a very, very long way to address the major contemporary challenges of the world. So in this context, to shape the future of chemical sciences and also the prepare chemical sciences to take on the new challenges. So this kind of dialogue and these kind of discussions, they are absolutely necessary. And the leading luminaries of chemical sciences, they can direct and they can orient the advances in chemical sciences for human development and also sustainable development. And we are hopeful that so this webinar will help in preparing and also shaping the advances in chemical sciences to take on these new challenges. So with this fond hope, I wish all the success to this webinar and also thank all of you for this wonderful opportunity. Thank you. Have a great day.
Thank you very much for kind words, madam. I'm sure this webinar will be helpful for the students in their career development. At this juncture, I should mention that we have entered into an MOU with VSKU University. In future, we'll be organizing many such programs in association with the university. Thanks, madam. Now, may I request our Honorable Chairman, Professor S. Ayyappan, for his presidential address.
Our colleagues from the Sri Krishnadevaya University, Ballari, Registrar Dr. Toshimala, the head of the chemistry department at the university, Dr. Lokesh, our distinguished guest this morning, Dr. Anand Halagiri, and Dr. Vadgaonkar, and many of the speakers will be coming in. My colleagues at the KSTA, Dr. A.M. Ramesh, the CEO of the academy, and Mr. Umesh and others, and our participant friends, student friends who have joined, nearly 100 of them for this webinar. To all of you, good morning. Welcome to this, this special webinar of 4 days on chemical sciences, advances in chemical sciences. At the outset, to all of you, 2021. This is the first webinar of this year from the KSTA. We are happy to join hands with the with the Krishnadevaya University. Thanks to all of you, and I'd like to specially thank our guest speakers, Dr. Anand Halagiri and others who are with us. Thank you very much, sir. And this webinar on chemical sciences, very, very important. I don't have to emphasize the importance any of these the new frontier sciences being so multi. Chemical sciences form the core of all the applications that we are talking of. For example, today the COVID pandemic, the way we are addressing the pandemic with several new generation vaccines and all that, at the core of everything, the chemical science, chemical portion, chemical aspect, biochemistry, biotechnology, whatever you call. So at every stage, these sciences have become so important. Our student friends have been studying some of these aspects in their classes, in their curriculum, but we thought in the webinar of this, it's really international with the speakers of the global, at the global level, who would bring in their insights, their experiences with regard to both the basics and the applied aspects of these different points that we are trying to address today and in the next 3 days. And since we will be listening to the keynote addresses by Dr. Anand Halagiri and others, I would not take much time. Once again, thank each one of you. Welcome you to this webinar. And request to the student friends is, we have, this is only the beginning. We request you not only to participate in this webinar, but to be in touch with the experts, to be in touch with the academy. We can, those who are interested in further research, we can be facilitating. Those who are interested in higher studies, we can be guiding with the help of the experts that we have today and for the next 3 days. So please be in touch. I'd like to really make a difference with regard to basic sciences in this country and particularly in the state of Karnataka. So you would not get a chance to hear, as was mentioned, these stalwarts in chemical sciences, very rare opportunity. Kindly make best use of it and be in touch in further times to come. With these words, once again, welcome and thank you very much.
Thank you very much, sir, for your presidential remark. I also take this opportunity to welcome Dr. Shiva Prasad of the Department of Chemistry, VSKU University. Welcome to you, Doctor. And now I request Dr. Lokesh for his vote of thanks.
Good morning, everyone. It is my great pleasure to thank everyone responsible for organizing this 4 days international webinar on advances in chemical sciences. This webinar is a convenient and suitable platform for our young minds to know the recent developments and achievements in the field of chemistry, and also it provides an opportunity for students to interact with the pioneers from the field working at national and international premier institutes. Some of the experts are delivering lectures of today's prime concern like drug discovery and renewable energy systems. The lectures by experts are expected to create curiosity among young scientists and inspires them to take up scientific career with innovative ideas. First of all, I would like to thank KSTA, Department of Science and Technology, Government of Karnataka, for organizing this wonderful and highly meaningful and informative international webinar on advances in chemical sciences in association with Vijayanagara Sri Krishna Devaraya University, Ballari. I thank Professor S. Ayappan, Chairman, Karnataka Science and Technology Academy, for his presidential speech and guiding us in organizing this webinar. I thank Professor Sidhu P. Aragur, Vice Chancellor of VSK University in absentia, and Professor Tulsi Mala Madam, Registrar of VSK University, and Professor Shashikant Udikeri, Registrar Evaluation of VSK University, for their kind support in organizing this seminar. My heartfelt thanks to Dr. Ramesh, Chief Executive Officer KSTA, who as always enthusiastically agreed and made all the arrangements for organizing this seminar. I must thank all the resource persons, Dr. Anand Halgeri sir, Dr. Prakash P. Vadgaonkar sir, Dr. Shashidhar, Dr. Taramani, Dr. Sharmishta Datta Chaudhary, Dr. Subramanya, Dr. N.V. Reddy, Dr. Nagaraj Basavegowda, for accepting our invitation and delivering the lectures. I also thank the Faculty of Chemistry Department, Professor Shiva Prasad, Professor T. Suresh, Professor Arun Kumar Lagasheti, who have supported in all the way in organizing this webinar. Finally, I should thank all the participants from Karnataka and other states who are eagerly and enthusiastically waiting to listen to the lectures from eminent personalities. Hope the lectures during next 4 days will inculcate scientific temper among students and they will have innovative ideas. Thank you.
Thank you, Dr. Lokesh, for vote of thanks, very cordial vote of thanks. Now let us start the technical session. We have with us eminent speaker, Dr. Anand Halgeri, sir. Sir, let us start your session. Before that, a brief introduction. Sir is a very eminent scientist Dr. Anand B. Halgeri sir obtained his Masters in Chemistry from the Karnataka University, Dharwad, and PhD in Chemistry from Bangalore University. He carried out his postdoctoral work under a UNESCO fellowship on industrial catalysis at the Chemical Engineering Department of the Tokyo Institute of Technology in Japan. On returning to India, Dr. Halgeri joined the newly established Research Center of Indian Petrochemical Corporations Limited, Baroda, Gujarat in 1976 as Vice President and Head of R&D Division of the Public Sector Indian Petrochemical Corporation Limited, Baroda, Gujarat. Dr. Halgeri provided sustainable leadership to the large number of scientists engaged in R&D activities. Later, Dr. Halgeri joined the Research and Development Center of Reliance Limited. He has very vast experience. Now, presently, Dr. Halgeri sir is working as Director of Purna Pragna Institute of Scientific Research, and he is coordinating the entire research activity in catalysis and material science and biological sciences. His area of interest include nanocatalysis, heterogeneous catalysis, mesoporous materials, novel zeolites, solid acid-base catalysis, industrial refinery petrochemical process, etc. For his vast experience and expertise, Sir has got many awards. He has published over 140 research papers in national and international peer-reviewed journals of repute, and also he has obtained 35 Indian and international patents. For his outstanding contribution in the area of heterogeneous catalysis for over 3 decades, he has been a recipient of many awards, including ICI India Limited Award of Indian Institute of Chemical Engineers, then Hari Om Ashram Award, Lifetime Achievement Award as eminent scientist in catalysis, and he is also the elected fellow of Institute of Chemical Engineers by Indian Institute of Chemical Engineers, Kolkata. He is also a recipient of KG Nayak Memorial Gold Medal of MS University, Baroda, and Sir has also been awarded Pride Citizen of Baroda in recognition of significant contribution for science and technology from Community Science Center and Rotary Club of Baroda in 2008. With this brief introduction, I request our Honorable Speaker, Dr. Ananda Rolgari sir, for his keynote address. Welcome to you, sir.
Okay, thank you. Check ಮಾಡ್ತಾರೆ. ಇದೆಲ್ಲ ಉಪ್ಪಿಂದಲ್ಲ ಮೇಲಿಂದ. Hello, good morning. You're listening, all of you. Good morning to everyone.
Good morning, sir. ಕೇಳಿಸ್ತಾ ಇದೆ, ಮಾತಾಡಿ.
Okay, thank you. I'd like to thank also Karnataka Science and Technology Academy for inviting a very important seminar and also share some of my thoughts of the recent work that has been done in this area. I would like to tell a little brief before I start on my topic of utilization carbon dioxide, how we can extract carbon dioxide, then how it can be utilized for various chemicals, fuels, and its application. And before I give a talk on that, I would like to briefly mention a little bit on the Purkala Institute of Scientific Research, where it is situated in Bangalore. This institute has about 25 doctoral students, and 20 students have got PhD degree in the area of chemical sciences and biology and theoretical physics. And it has published more than 300 research papers, and more than 20 students have got PhD degree in the area of material science and technologies there. And we have set up a very advanced research generated by Professor in the area of advanced catalytic materials there and its application to various chemicals there. Our institute has got several awards from various of chemical sciences, and also have published more than 300 research papers in advanced chemical research journals. And a group of 7 faculty and students have been working in the various areas of material science. The institute has been working on both applied research as well as the government-sponsored research. We have got a grant from many US companies, Shell Company, Hindustan Petroleum, Thermax, Deepak Nova Chemicals, many of them. And similarly, we have several government-sponsored projects, about 23, as well as 17 industry projects we have been executing as a part of a research program. Our institute has got fairly a good analytical center, which is required for our master course student and doctoral course student. The idea is to share some of this information. Some of the students who work in Ballari University can think of working at our institute for a project work, or even to carry out some doctoral program at our institute at any time of their interest there. You can provide for carrying out research, and the degree is awarded by the Manipal University of Mahe there. This is a research institute, and now I would like my main topic. I would like to give the outline of my talk. First is the introduction, emission of carbon dioxide, flue gas, then comes the carbon dioxide capture strategies with examples, and carbon dioxide valorization to chemicals, PPSR, and then finally conclusive remarks there. Okay, I think this is the carbon dioxide emission all over the world now. To per country, per percentage of from the AVO sector, basically come from maximum from China, then USA, and followed by several other countries. Emission, and then the rest of the world is 25.6% emission is taking place. International energy CO2 emission from fuels combustion highlights there. Emission of carbon dioxide from several industrial sectors there. This is again how rated. The first one is from electricity generation in heating, is around 44%. 18%, fuel consumption, and it is around 12%, road transportation, and then cars and other vehicles 16, and other non transportation sector is around 4%. So this
Sir, excuse me, change that slide.
hello?
Slide.
Okay. Yes. This is okay. Carbon dioxide by activity sector. Various sectors we have presented. One is electricity generation, use maximum CO2. Then manufacturing 18%, fuel consumption 12%, 6% is road. So this is the overall CO2 generation from various industrials.
Sir, sorry to interrupt, sir. Umesh here from KSTA. The slides are not changing, sir. Please update, sir.
Now, are you able to see the slide, sir?
Yes, sir. It was fine, but now the presentation has gone.
I'll show you.
Yes, sir. No, it's perfect, sir.
Okay.
Yes, sir. Yes, sir. Yes, sir. It's okay, sir. Now. Thank you, sir.
Okay. Very good. I have given the various carbon dioxide from various industrial sectors, not only from transportation, but many industries use a lot of carbon dioxide. One is ethylene oxide plant gives you around 10 to 15 million metric tons of carbon dioxide. Ammonia produces 160. LNG sweetening is 25 to 30%. Ethylene, mostly from petrochemical industry, you can see so much emission is there. Fermentation industry, iron steel industry, oil refineries also gives around 900 million metric tons carbon dioxide. Cement industry is also more than 1,000, million metric tons of carbon dioxide is produced per year. So you can see a lot of greenhouses coming out of from various sectors there. Carbon dioxide is emitted. How one can make use of carbon dioxide for various applications? So I have given is yearly, if you look around, 24 carbon dioxide were annually produced on the earth as a result of human activity. From these fuel, the thermal go back. And that CO2 produced one can use through photosynthesis. The amount of photosynthesis carbon dioxide is oxygen and this thing, but this amount very little than what to produce carbon dioxide from various sectors. So CO2 is consumed through photosynthesis very little, but still large number of carbon dioxide produced in human activity. Flue gas is where the thermal power plants are there. It emits lot of CO2. That is the nitrogen, carbon dioxide, water are the major CO2 generating. 73%, and followed by NOx, SO2, carbon dioxide is on 16%, water is 5 to 7%, oxygen, flue gas composition, and one can extract CO2 from this flue using the kinetic diameters. If you look around, CO2 has a kinetic diameter 376 and nitrogen 3.64. One can have a molecule is used and can extract CO2 can be recovered. Various absorption techniques there. Let us look. I have presented in the first part of my talk how CO2 is produced in various activities from industry, from fuel, thermal power plants, and the consumption of CO2 conversion into through photosynthesis is very little, but still large number of green gases is still is exposed to the environment there, which is very detrimental there. The next question is how one can use CO2 and how we can capture that and how we can make carbon dioxide useful to various chemicals and fuels which are more application oriented for human beings. There are two aspects of technologies are available associated with CO2 separation and capture. One is absorption, another is adsorption there actually. Absorption is solvent scraping. You take monoethylamine and then you absorb carbon dioxide, and then the other is adsorption. Adsorption means you can use carbon, alumina, zeolites, and molecule MOFs material. These are all adsorbents where you can carbon dioxide is adsorbed and then it can be reused for various applications there. This is liquid phase, another is heterogeneous. Then what materials we can use for absorption of material is one is porous material there. I would like to define classification of porous material. They can be used for liquids as well as for the gases there. For all the postgraduate students, pore size is in case of porous material is microporous and macroporous. It depends on the size. Macroporous is less than 2 nanometers. Material like zeolites, jettison 5 material, 2 to 50 nanometers is MCM40 type of material. Then if they are more than 50 nanometers, macroporous, they are all sponge material. This is as far as the solid catalysts are. And then we can also use the building framework using organic, hybrid, and inorganic materials. In organic, there are a lot of porous polymers are also there. We call POP. And then in hybrid, you have got both organic and inorganic framers material. I think these are the class of high porous material now emerging as a new novel material in the area of advanced material science there. And then we have got a lot of silica and other materials are also being used. Why porosity is very important? It has got large surface area, accessibility, and residence time, and we can disperse on these porous materials there. So it has got a lot of advantage and it can give you varieties of applications. Global capture of carbon dioxide technologies, the global carbon emission is 400 ppm. The top countries capture CO2 highest States, China and Europe, and these are the major contributions for CO2. One can directly air capture through techniques, but they have got limited application, so it's not fully utilized for many applications. And the best way is to direct air capture through sorbent-based. Sorbents are there. One is absorption, another is adsorption. How to design the material for principal criteria for designing an ideal sorbent for carbon dioxide. CO2 sorbent, we have to design. What is most important is you should have high adsorption and selectivity. You should have high thermal water stability. It should be rate of uptake should be much more, and material can be recycled and more cost effective, and you should have heat of absorption should be minimum. So these are the principal for ideal adsorbent to capture carbon dioxide from the atmosphere. For adsorbent, we can use sodium aqueous hydroxide. We can make calcium sodium hydroxide, potassium hydroxide can be used for absorption of carbon dioxide. Solid alkali carbonates are utilized. Then comes organic, inorganic hybrid compounds like polyethylene silica and metal organic framers also can be used for capturing carbon dioxide. This is some kind of a mechanism how to capture CO2 in aqueous amine solution. These are all monoethylamines and triethylamines have been utilized for CO2 is absorbed on methylamine, and then it can be extracted later stage. And similarly, this is the mechanism. Methylamine, it forms carbamide, and similarly tetraethyl forms the bicarbonate. So these chemicals can be obtained using carbon dioxide, water, and it has this kind of mechanism has been there. There are some drawbacks for amine solutions. Basically, they are unstable towards heating. When you want to CO2, they become unstable, and then these are also highly corrosive, and its gravimetric uptake is only 14%. So this is in industry, especially in petrochemical industry, refining industry, where CO2 they are also using scrubbers, using methylamines to remove CO2 there, but got certain drawbacks, not fully exploited in many places there. The other class of compounds we would like to bring to our kind of attention is metal organic framework structure for CO2. MOFs have become novel materials there. The history of first publication came in Nature 1999, and the last 20 years there is a lot of work has been done. Metal organic framework structure, porous material constructed by joining metal containing units, building reticular bonds. This is the organic linker, this is the metal, and it forms the metal organic framework structure. Various linkages are, and similarly organic linkers, varieties of organic linkers have been utilized there. Secondary building blocks to make them MOFs, published by Kitagawa and from Japan in 2004. So if you look, these are all properties of metal structure. These are all active sites. Secondary building units are this. They are all semiconductor clusters, organic linkers, and pore volume. The molecules have large pore volume and a very high surface area of nearly 2,000 metal organic frame structure, where people can absorb and can be absorbed easily, and we can get use as a CO2 absorbent material. And these are all certain advanced material used for extraction. One drawback with MOFs is if water is there, this goes out, although it has a thermostability of 350 centigrade. But one drawback, they are very potential carbon dioxide absorbent, but if moisture is there, it loses its stability. Then advanced for varieties of purpose. In Pune Institute of Scientific Research, we have on this new material called MOFs. MOFs can be used for heterogeneous varieties of application. The work we have published in Chemical European Journal, and then used for carbon dioxide adsorption and desorption, and then we have MOFs for gas sensing, especially when carbon monoxide, sulfur dioxide, NOx material at ppm level. If you want to detect that, MOFs can be utilized for detecting this material there. And we have built a good school of research, and work is being done, and we have published this paper in Chemical European Journal, Delta Transaction, and several work application of MOFs for heterogeneous catalysts as well as gas, and also for CO2. I have given the first part, varieties of carbon dioxide extraction, and after getting carbon dioxide captured, how one can utilize various applications. That is the second part of my talk. This is captured carbon dioxide, which is now here in this circle. It has got two applications. One can use for fuels, and can use for food. I'd like to give some summary of captured carbon dioxide used for flavors and fragrance material, and then carbon cannot used for carbonates. Captured carbonate can be used for chemicals like methanol, urea, and carbon monoxide and methane. It can be used for fertilizers, and it can be used for refrigeration. Dry ice, if you look, it has got at -60 centigrade. You can use carbon dioxide. And carbon dioxide is also used for certain distillation process of late now. And then miscellaneous. It can be used for metal casting, added medical facility, aerosol, dry ice, like that. It has a lot of application for in the area of fuels there. Then it can be used for protecting carbon-fired shield gas welding. As far as this part is completely fuels. Then let us look at the food part. Carbon dioxide can be used to make carbonated beverages, food products there. It can be used for enhanced recovery of fuel recovery, especially in oil and gas recovery. They use carbon dioxide to recover oil and gases there. And it has a lot of potential application refining industry. Then carbon utilized to make plastics. Polymers can be made from the captured carbon dioxide, and this is also used for fire suppression. Where there is fire extinguisher, it contains a lot of CO2. So now becoming important. The idea is nowadays there is an international takes place on carbon dioxide capture and its utilization. The idea is CO2 is available. It doesn't cost any cost for that, which is coming from the nature, and how one can utilize carbon dioxide for human beings and various applications. Among that, the next part of my talk, how captured carbon dioxide can be utilized for various chemicals and its application. These are, one can use carbon dioxide, making use of catalysis, there. And these, I don't want to go in details, the number of reactions are there. Carbon dioxide and hydrogenation to give methanol, carbon dioxide to varieties of materials can utilize, which are been published in chemical review. So application of to chemical is a very important area, so that the raw material is available CO2 and one can convert it into various. Of application of carbon dioxide, materials can be synthesized, and these are also produced very industrial. The next question is how to use in catalysis to fixation on this material is most important from the application potential and how to activate. This carbon dioxide is difficult to activate because on a catalyst surface you need two kinds of acid sites. Lewis acid and Lewis. CO2 activated into valuable chemicals when it reacted with the molecules containing electron or active hydrogen. These electronic donors like Lewis acid base are important, and hydrogen activate. Once it is activated on a catalyst surface, you will get absorption, and then you can react on the surface, and it can be varieties of chemicals out of the system. Then the application I would like to present is how to synthesize urea using carbon dioxide. Urea based on carbon dioxide, then urea excess of ammonia is formed, carbonate is formed, thermal treatment, water, ammonia and carbon dioxide, which is evaluated and then recycled, and then thermal concentration, urea, once it is produced, it forms in the granular urea, which is used as a fertilizer. You know, urea is extensively utilized as a urea fertilizer industry, and is mainly coming from carbon dioxide. There is a utilization of urea has increased from 200 to 260, and carbon dioxide is also available as a byproduct, which is there. So schematic representation of urea synthesis from one of the important applications. Then let's move into some salicylic acid. Conventionally, it is done by organic chemicals. So we can take then carbon dioxide. We can make salicylic acid using the system. Similarly, inorganic carbonates, calcium carbon dioxide, and then calcium oxide forms the calcium carbonate. Then formic acid. Formic is also one of the important chemical. Currently is made in BASF technology using and acetic acid forms, and this is very complex process. They use CO2 based approach to make direct reaction, making hydrogen, carbon dioxide, straight away formic acid. Improvements have taken up in CO2 hydrogenation. You can use some metal complexes using homogeneous catalyst there. You can make formic acid. And commercial process. A lot of work has been done on the lab scale. People have published several papers on ruthenium complexes, iridium complexes to make a form using CO2 hydrogenation. Oxide to methanol. Methanol is produced through the Fischer-Tropsch synthesis, but one can carbon dioxide to hydrogenation to produce it. Varieties of processes for making, paraffin, olefins using, a variety a TiO based catalyst system at a temperature of 300, very high pressure, is around 60 to 70%. You get methanol as well as olefins. Then background, we have also attempting some research work in the area of carbon dioxide. This is national importance because how we can use waste material like carbon dioxide into valuable chemicals. Currently, we are all making from petroleum resources, all these chemicals. Petroleum resources, which is our varieties of chemicals. Work we application to make methanol from carbon dioxide. Methanol has a large application. Fuels, you can make gas, biodiesel, you can make dimethyl ether. Cells, methanol can be converted. That is there. Methanol component, and currently it is made from the which is very cost effective. Somewhere around 1000 degrees centigrade, the reaction is carried out. The alternative use is how we can use carbon dioxide to hydrogenation to make methanol. Methanol for the 100 tons in the year 2020. Methanol is an important requirement is increasing year. So methanol is government. I would like to give production of methanol. Current methanol is produced by the natural gas, biomass, and coal through syngas. I was telling syngas, carbon monoxide, hydrogen to produce methanol using Fischer-Tropsch synthesis. Fischer-Tropsch, these are the German scientists who won the Nobel Prize making for methanol in 1950s, and it was one of the major discovery of catalyst research is how to make methanol from syngas synthesis. And the other approach which we are thinking is how we can use carbon dioxide to make methanol, and this is the most challenging topic, and a lot of work is being done. As I know that methanol is used for jet, and you can also use for varieties of chemicals like ethylene, polyolefins, acetic acid, methyl acetate, and all these have chemicals also can produce from methanol, CO2, hydrogenation methanol, and you can produce this kind of a fuel material. This is the technologies used for Fischer-Tropsch synthesis. They use methane and steam before at 1000 degrees centigrade. It produces syngases, and you can produce methanol reactor, and you can get methanol monoxide and hydrogen. This is called Fischer, which is worldwide when can be utilized, and then you can send it for distillation. Methanol is separated and water comes out of that, and methanol is now currently large quantities have been produced through syngas synthesis. Now following apart from syngas is in the current research of production from carbon dioxide hydrogenation institute is from the various thermal plants and this thing, and we can capture CO2. Capture CO2 is here. This is the reactor, catalyst reactor, where you can activation of CO2 plus hydrogen. Hydrogen we can generate through photocatalysis. Now photocatalysis is very important subject. We can splitting, we call as photocatalysis. You can do photocatalysis, water splitting. You produce and oxygen. This hydrogen produced from the photocatalysis is again reacted with a catalyst. One is carbon dioxide stream. Another is basically photocatalyst hydrogen, and it reacts on the catalyst and it forms olefins and aromatics are being produced. And catalyst has been have been well, and still work is going on in this area. The catalyst system used for CO2 to methanol, large number of catalysts are used: copper, zinc, gallium zinc oxide, and several mixed oxide used. And the conversions are around 99%, but select very poor. And still a lot of research work is going of finding a better catalyst to make CO2 hydrogenation to methanol under very high conversion. This has been published in recently in reviews. Example, there is a commercial plant available for carbon dioxide, which is called George CO2 renewable methanol plant in operation in Iceland. Nearly 50,000 million is produced from carbon dioxide to methanol. George won the Nobel Prize 80, and they have set up a plant, his own plant in produce methanol. The hydrogen and carbon dioxide reacted to produce methanol. This is one of the important milestones of making methanol from carbon dioxide. Then we can switch over to other areas apart from methanol. Epoxides can be reacted with carbon dioxide. You can make cyclic carbonates have a lot of application, excellent property polar solvents. Electrolysis and secondary batteries. It can be used for polycarbonates and other polymeric material. Used as a production for pharmaceutical material. So these are all very cyclic carbonates made from carbon dioxide and reacted with epoxide using some. Institute of Scientific Research, we have been working on how to carbon dioxide with epoxide to make cyclic carbonates. We have used several like manganese, barium, tin, nickel oxide, various composition. We have carried out mixed oxide catalyst systems to make cyclic carbon using this catalytic material and using binary mixed oxide, like iron, cobalt, copper, and zinc. But we found the best one, manganese and barium. Catalysts have given the best yields of cyclic carbonates. Basically, tin nickel oxide gives highest propylene carbonate at PC around 73% yield, and then around 68%. These are got potential application, and this work we published the carbon dioxide utilization. Let me tell you, there is a journal now, application of carbon dioxide utilization. See how much work, research work is going around the world. Utilization. Now they are publishing an international journal called Journal of Carbon, and we publish this novel work, how we can make basically polycarbonate using some binary mixed oxide catalyst. Spectroscopy studies, what are the important centers present on, as well as nickel tin catalyst system. These are our scanning transmission electron microscope. The catalysts are spiral in nature, published in Journal of Carbon Dioxide Utilization. Portion of this catalytic To understand the pore size distribution, the measurement, these are the surface area and pore size distribution material. And nickel tin oxide shows type 4 the absorption isotherms and average porous macroporous materials of 40 nanometers length there. So these are the important class of material used for carbonate synthesis. I've also done a lot of cyclic additions of using carbon. Again, these varieties of organic reactions using using nickel tin oxide catalyst were tested for different epoxides and CO2 reactions. Among the oxide, the product will decrease in the order of propylene oxide, epochlorine oxide, and cyclohexene oxide. Propylene oxide, epichlorine gave highest cyclic carbonate and catalytic activity, and these have been given higher, and this work has also been published. Then we can come to ammonia, to carbon dioxide, cyclic urea. Cyclic urea class of carbonyl compound and usual chemical intermediates in the synthesis, agriculture chemicals, as well as dyes, as well as antioxidants in gas additives. These forms a very important application and can make using carbon dioxide and cyclic urea material there. As cyclic motifs frequently observed in biologically active and in particular 6-membered ring ureas are important, 6 to 9, because of their activity, antiviral, anti-rheumatic activity. So these are materials for varieties of applications. Basically, from Japanese scientists, they have been able to use pure oxide has found to be the best catalyst for this kind of reactions. Found to be best catalyst for making. The next class of compounds which we did in our institute is a basic material called chloride supported and alumina and water. This is done by impregnation, metal impregnation on alumina, which forms a slurry, and dried at 120 degrees centigrade. Potassium fluoride is absorbed and then removed and washed. It forms a mixture of zinc oxide, potassium and alumina. Then it forms a slurry, and then activation use the final material there. Bohemite was at 500 degrees centigrade for hours on alumina catalyst. Alpha catalyst, different weights of percentage of zinc oxide, potassium were loaded on a gamma alumina wet preparation method. And this is very new class of basic compounds have been utilized in varieties of application. This work was published in by Dr. Shanba and Kular on the applied catalysis journal. Using extradite method and then absorption properties of alumina, fluoride and alumina catalyst, zinc oxide, potassium alumina catalyst have shown the better characteristic profile. We also utilized to go for more iteration using X-ray photoelectron spectroscopy, showing what are the activities on the surface, the level of oxidation states of this zinc on the surfaces, and tetrahedral octahedral structure there. This zinc oxide, potassium fluoride on alumina, we have used for making propylene carbonate, and it has given KF on zinc oxide. This zinc oxide, these are two classes, and they are given a very good performance in terms of conversion, 72%, 60, 20 observed for this propylene carbonate. And then we have, these are all done. Once you use a catalyst, we wanted to see the recyclability. How can you use the same for making this material? The first run gives you very good selectivity of 90% and around 85% selectivity, and then second run, third run, and fourth. After fourth run, the catalyst can be recycled and used very extensively and change in the crystal structure after and before use. After fresh catalyst condition, marginally decrease in the conversion by 3%, which is probably due to the deactivation of the activity, which could not be regenerated with regeneration. Later on, the activity remained almost less than 0.2 and 1.5% variation yield, also selectivity from the second cycle. So these are all zinc oxide, potassium chloride, and very potential catalyst for make propylene carbonate, which has good application. And we will take the last use of making urea from amine carbon dioxide. You can take dibutyl urea and then carbon dioxide and butylamine. You can make important class of carbonate compound for chemical intermediates in the synthetic form. This product is mainly used in varieties of kinds of formaldehyde and agent compounds. One can use, use CO2 for this kind of application. We have done some work on this area using the tin and nickel mixed oxide catalyst for synthesis of 1,3 urea, and these are the position, and they have found dibutyl urea. To give the work, CO2 utilization work carried out at Pune scientific researches, cyclic carbonate synthesis, and using manganese barium mixed oxide catalysis, found to be recyclable, high yields and high selectivity, and it has been very potential and what we have been published there. Then comes CO2 hydrogenation to olefins. Currently, olefins are produced in petrochemical, but one can make olefins from carbon dioxide hydrogenation to methane. Olefins can be produced there. Then the important third important factor is you can take methanol and carbon dioxide to make dimethyl carbonate. Molecules of methanol reacts with carbon dioxide on a catalyst to produce dimethyl carbonate in water. Carbonate is also very important chemical for varieties of application. These are the three reactions have been completed and some are there. Then we also attempted to make urea cyclic urea synthesis and using carbon dioxide, as a, and one can make a lot of industrially important chemicals and fuels. The last one is to hydrogenation to methanol. This is a very important and challenging topic. Methanol has been defined as of the energy new material by Niti Aayog. Methanol to be produced in this country because methanol we can use in biodiesel, methanol can be used for dimethyl ether. Methanol is an important chemical. Currently, India is importing a lot of methanol from around the world. So one can make methanol from CO2 is an important application. And this group of scientists which I'm showing here, Dr. Shanbag, and these are a group of scientists working on a pilot plant of developing carbon dioxide hydrogenation using the best catalyst to make methanol. And this project, chemicals making from CO2 along with methanol, has been supported by Karnataka government. Group of Science and Technology, all of you know, is supporting lot of research activity for many people here, and we are fortunate to get big grants from Vision Group of Science and Technology to carry out to make chemical from carbon dioxide, and also a very important national project called synthesis by Hindustan Petroleum Corporation in Bangalore, because the refinery evolved a lot of carbon dioxide. The whole idea of refinery is how we can make use of carbon dioxide to make methanol. So Hindustan Petroleum Corporation Research and Development Center have asked us to take up a project to how to convert methanol. So from CO to hydrogenation, this still work is going on, and if we can make at the pilot scale level, and is an important topic from energy point of view. to make a concluding remarks now. We have spent more minutes now. Concluding remarks, the utilization of carbon dioxide strategically can be effectively combined with fossil carbon, ensuring the availability of carbon and for a longer time avoid volumes of CO2. Awareness about CO2 pollution and global warming. Chemical transformation of carbon dioxide is strategy. Chemical transformation of carbon dioxide strategy effectively should be utilized to make value. It needs very efficient catalysts for these reactions. Hence, there is a lot of scope for catalyst research for the development of chemicals and fuels. Catalytic carbon dioxide hydrogenation is challenging to make more chemicals like higher alkene. We can make olefins, we can make methanol, make formic acid, formaldehyde, which can be given more importance among reaction there. That is important for catalysis researchers to dedicate the research in designing efficient catalysts for CO2 transformation. CO2 is available from waste to chemicals transformations one can do with using CO2 and to make something out of that. So this is the whole theme of my talk. I hope I was able to give some thoughts on 3 areas. CO2 is available plenty in this. One can extract. There are a lot of techniques are there how to extract CO2. And after extraction CO2, it can be used for fuels, it can be used for food items, and how one can the fuels are concentrated and how one can make chemicals. The work done at around the world and the work done at the Purnapula Institute of Scientific Research. I have also tried to highlight it. The application of catalysis has become an important subject in converting CO2 to hydrogen and CO2 to variety of chemicals using novel catalytic material there. I would like to acknowledge my colleagues, Dr. Ganpati Shanbag, who have led the team, the group of young doctoral students on this area. And I would like to thank the organizers of the International Web Seminar, particularly Dr. Ramesh, for advances in chemical science. And with this, I would like to conclude my talk. Thank you.
Thank you very much for very insightful, very informative talk, sir. It was really exciting. I'm sure students would have got sufficient take-home message from your talk. They will. Are there any questions, please, from participants?
No, sir.
Okay.
As of now, there are no questions.
Sir, offline we will take questions.
Okay.
Your talk was in a very simple language. I'm sure most of them would have understood what you told. I'm very, very thankful to you, sir, for your kind time and participating in this particular webinar. In future, we will be organizing offline physical meetings in our campus. You have already seen our campus.
Sir.
We will be inviting you for talks. And one more thing, sir, we have been entering into MOUs with various institutes across Karnataka. I also request you to kindly consider entering into MOU with your institute.
I'm glad, Ramesh, you brought this. I was thinking on the same line.
Yes,
because
sir.
you have done it several places. It's a great honor if you can sign MOU with your.
Yes, sir. Please,
I'll come to your office one day and find it. Okay.
Yes, sir. Please, sir. Very kind of you. Thank you very much, sir.
Okay, thank you. Bye.
Now we have with us Dr. Prakash Vadgaonkar, former chief scientist at NCL Pune. Prakash, sir.
Just a moment, Rameshji.
Yes, sir. Yes, sir.
Can you hear me?
Yeah, sir. We can hear, sir.
Okay, great.
Your presentation we can see, sir. Let us see your.
Just a moment.
Yes,
Okay, okay, Ramesh ji. Yeah, I think, yeah, please go ahead.
Yeah, we have with us another distinguished chemistry eminent scientist, Dr. Prakash Wadgaonkar, is the emeritus professor scientist at Polymer Science and Engineering Division of SKL Pune. Sir, current research interests of Dr. Prakash Wadgaonkar sir are controlled polymerization methods, monomers and polymers from renewable resources, high performance polymers, polymers for optoelectric electronics, associating polymers, polymeric materials for gas separation studies, etc. Dr. Prakash Wadgaonkar obtained his PhD from University of Pune. Then he has a very vast experience. He started his illustrious career as a senior scientific assistant at NCL, and till June he held various important positions in the NCL. Now, since June 2019, Sir is working as emeritus scientist at the Polymer Science and Engineering Division of NCL Pune. Again, Sir has been awarded with many awards and honors of repute. Few of them are Jeevan Gaurav Puraskar, that's Lifetime Achievement Award in 2017 by Solapur University, Solapur. Then NCL Research Foundation Scientist of the Year Award in 2013. He is also the Fellow of Maharashtra Academy of Sciences, and he also has obtained Professor M. Shantappa Silver Jubilee Award in Polymer Science for the year 2006 by Society for Polymer Science. Then again, he is also a recipient of Sukumar Maiti Polymer Award 2004. In addition, he is also a recipient of CSIR Technology Award in 2003. Dr. Prakash sir is a member of various committees of national level and state level. He is a life member of our Polymer Science Society. He is the co-convener of SPSI Macro 2018, and he was a visiting professor of LCPO University Bordeaux, France, and also visiting professor at Institute of Charles Gerard Montpellier, France, and he has also visited Sydney and Nova Scotia as a research scientist. Professor Wadgaonkar also has consultancy assignments with various industries, and he is also on the editorial board of very reputed journals. He is a guest editor of Green Materials, ICE Publishing, UK. He is also a member of editorial board of Green Materials, ICE Publication, UK. He has published over 215 articles and research papers in various journals of national and international repute. Sir has guided 20 PhD students, and currently 4 PhD students are working under his guidance. He has visited many countries across the globe. With this brief background, I welcome Prakash Wadgaonkar sir to deliver his talk. Welcome sir, how are you?
I'm fine, thank you. Good to see you, Dr. Ramesh ji.
Thank you sir.
Yeah.
Please take over.
Thank you. Greetings from Pune. At the outset, I would like to thank Ramesh ji for the very generous introduction, and I'm grateful to KSTA for inviting me to participate in this wonderful conference. So thank you, Ramesh ji, and your team, for inviting me. So what I would like to do in the next 45 minutes or so is to talk to you about one important area in the field of chemistry. That is how to derive sustainable chemicals based on byproducts of agro-processing industry. And I am also thankful to Professor Anand Halgiri for setting the tone for this presentation. He definitely touched upon a very important topic about CO2 utilization. Okay. So what I'm going to do, actually, my presentation is actually divided into two parts. The first, 20 minutes or so, I will actually talk about the philosophy or the motivation for undertaking the work. And in the later part of my presentation, uh, what I will do is also share some of the exciting results from my research laboratory. And the idea here is to, convey the excitement to the students who are attending this conference, and how one can be creative, how one can be imaginative. Rameshji, there is some disturbance in the noise. There is some noise coming back in the background.
Sir, I will mute it.
Hello?
Rameshji,
can you hear me?
Please continue. We can hear. Please continue, sir.
Okay. Yeah. So what I was telling, the presentation is actually divided into two parts, and the first part of presentation will be, just to put the subject in the right perspective. So I will introduce the topic and also tell you the motivation, behind undertaking the work, which I'm going to present in the second part of my presentation. And the theme of the presentation is how one can make, chemistry sustainable. Okay. As you know, chemistry is the mother of all sciences. Okay. And chemicals are very important. In fact, there will be no life if there are no chemicals. In fact, we cannot imagine the modern world without the materials. And materials are nothing but, basically they are all, chemicals. And spectacular developments have taken place, over the last 300 years or so in the field of chemical sciences. Okay. And as you know, the life expectancy has gone up, and now people live longer, and thanks to the, new versions of drugs and pharmaceuticals. Okay. The agricultural productivity has gone up, so that's how it is possible to feed the population, the world's population, which has been growing. So this is again possible because of the new versions of fertilizers and agrochemicals, etc. And there is no undenying that the life has become more comfortable. The modern life has definitely become comfortable, and we should all be grateful to all the scientists and technologists who discovered several new chemicals which are we use in our day-to-day life. And we also use materials, like I said, in fact, we live in the world of materials, and these materials are derived from chemicals. I just want to take you back to the periodic table. As you know, there are a certain number of elements, and from these elements, the lot of chemicals are made. In fact, and like I said, chemistry is actually a mother of all sciences. It is central, useful science, and it's creative. Meaning, chemists have created new materials, which did not exist in the nature. We call them as the synthetic materials or synthetic chemicals, which have been created with some purpose. Okay. But also there is a downside to this. In the whole process, the chemists or the engineers or the technologists, they made these chemicals with good intentions. Okay. Of making the life more comfortable, making the life easier, to increase the lifespan of the human beings. But there have been some regrettable consequences of this also. Of course, this was not done with intention, but in the life there are certain good ideas, or good intentions which go bad. Okay. And one of the example is, a lot of environmental issues have been created by the production and excessive use of chemicals. And one of the chemicals, which has been highly talked about is the carbon dioxide. And Professor Anand Halgiri gave a very nice introduction to the subject and how chemists are tackling to utilize excessive carbon dioxide. So friends, what I want to just tell you, what we have done so far is, the reaction of hydrocarbons to carbon dioxide. This is the wasteful reaction which we have done all these years. And I'm going to tell you, little more details about that. And now the chemists of the next generation, what they have to do or what they should be engaged in, how can we convert, this carbon dioxide back into the chemicals or hydrocarbons, and in fact, this is $1 million question, and I'm sure, the next Nobel Prize will be for, if somebody comes up with an idea how to fix carbon dioxide or, convert carbon dioxide into useful chemicals, So this is the most interesting topic, most, challenging topic, to work on, to utilize, use carbon dioxide as the starting material and derive the chemicals. So what I was telling,
Sorry to interrupt, sir.
Hello?
Sir, sorry to interrupt. Umesh here from KSTA, sir. The slides are not changing, sir. You have to
No, I
keep
have
the
not moved
slides.
any slide so far. I'm still on the first slide.
Done, sir. Done, sir. Okay, sir. Thank you, sir.
Okay, okay. I
Sorry
was
for
just,
the interruption.
telling the, philosophy, okay. And the friends, again, another one more issue is that, we should live with nature and not against the nature. I think, this current pandemic, the corona, has taught us this, that we should live with the nature and not against the nature, okay. So we should live in harmony with the nature. And that's why, the concept of environmental sustainability, okay. The sustainability in the production of chemicals comes into picture. And another topic which I'm going to touch upon is the, how one can utilize byproducts of agro-processing industry. The chemical industry of today is basically a petrochemical industry. All of these chemicals, materials, solvents, dyes, pharmaceutical, which we make use of, they're all derived from petrochemical resources. And as you all know, these are non-renewable resources, meaning there are finite resources of these chemicals, and we cannot depend on these chemicals for indefinite time because there are limited stocks, and the rate at which we have been consuming these chemicals, the day is not very far when we will not have any of these chemicals which we use as the starting materials. In fact, the entire chemical industry is based on this petrochemicals. Now the question is, if you don't have petrochemicals, where all these chemicals will come from? Okay, so the obvious option is to go for waste products of agricultural industry. As you know, though a lot of developments have taken place in the field of chemistry and technology, or for that matter, all sciences, we still cannot produce food in the laboratory. Food actually is produced majorly. Of course, there have been some developments wherein people have been able to make artificial meat, in the laboratory, or have been able to make proteins from carbon dioxide. But these are, just laboratory curiosity, and the commercial production is very far. Okay, so as of today, and over the years, we, human beings have relied on agricultural resources, for the production of food, and which is very essential for our survival. So agro industries will be there. So, but when you want to derive food from agricultural products, there is also some waste products which are generated. So now the question is, can we take or make use of these agricultural waste products and convert them into the chemicals or materials which we have been currently deriving from petrochemical sources? Okay, so these are the two underlying themes of my research, like how we can make chemical industry which is sustainable. It's definitely true that today's chemical industry is not sustainable. It is so the question is, how can you make the chemical industry sustainable, and how can we get away from petrochemicals and rely more on agricultural waste products? So this is the theme of my presentation. And of course, friends, again, one must remember that if we destroy the environment of this planet Earth, there is no other place for us to live. Okay, the humans can live only on this Earth. So it's imperative that all of us actually be concerned about the health of this planet, that is the Earth. Meaning we should not destroy the environment. Okay, by our acts. And like carbon dioxide generation. This has really created a threat to the environment. Okay, and in fact, they say that the world will come to an end, if we keep doing the things the way we have been doing. So there is no scope for business as usual. Okay, we must definitely do some introspection, take a break, and find out exactly what things we are doing wrong. And I think the time has come where we need to reset the button. Okay, and be on a different path, of sustainable production of chemicals. That's, I think, the order of the day. Okay. So with this brief, preamble, let me go to the first part of my presentation. Where I'm going to tell you, like I said, science and technology, spectacular developments have taken place. And the first technology, if we can think of, is the agriculture. Actually, it's a systematic way of doing the production of, food. And then, there have been various stages in the history of human development. And just the point to be noted here, all these ages are known by the materials which are prominent in these particular ages. So that's the important, that materials are very, very important parts of our integral parts of our life. Okay. So initially it was Stone Age, Bronze Age, then Iron Age, and in the modern age we call is the age of plastics or polymers. Okay. And you can see there are several technological developments, which have taken place, like industrial revolution, like they call industry 1.0, and now currently we're talking about industry 4.0. So the science and technology is, very, very important. And they say that, today's science is the technology of tomorrow. Okay. And tomorrow's problems cannot be solved with yesterday's science. Okay. So we need to develop definitely new science and new technology, And of course, as you can see here, materials are very important throughout the history of mankind. Okay. So that's the, importance of chemicals and materials. But like I said, again, we have depended so far on petrochemicals, for deriving these chemicals. But the point to be, noted here is petroleum is not an inexhaustible source. There are limited resources, and it's becoming more and more expensive. And it is also not distributed evenly. There are only certain countries who have got the oil reserves, and certain countries, like India, also we have to depend on the import of oil. Okay. And another important point is, the burning of petroleum products, including plastic, has an impact on the climate change. Okay. And you can see the release of carbon dioxide in the environment, causes increase in the temperature of the earth. So these are some of the issues. Okay. Now I was talking about, chemicals are integral part of our life, and chemicals are used, in various sectors. You can see here energy sector, household, transportation, everywhere we make use of chemicals. I will not get into all those details, but if you talk about, there are only 70,000 plus chemicals. Okay. Though chemists have made 88 billion compounds, new compounds, which never existed before. As you know, in the periodic table, there are only certain number of elements. But from that element, using the creativity and imagination, chemists have produced in the laboratory several chemicals. But 70,000 plus chemicals are of, of industrial relevance, so to say. Okay. And when we talk about, organic chemicals, there are basically 7 basic building blocks, like ethylene, propylene, methanol, xylene, benzene, toluene, butadiene. These are the, some of the important chemicals. And from these chemicals, all of these, drugs, pharmaceutical, dyes, monomers, solvents, all those can be derived, by some synthetic transformations. Okay. And if you look at the, the share of basically the plastic or chemical industry, it's only hardly 10%. The petroleum resources are used by chemical industry. The major share is by, energy industry and transportation industry. As we know, we live all in an energy-driven world, and in energy, today's energy mostly comes from these, petrochemical resources. Of course, scientists are trying to, find alternative or renewable resources of energy, like harvesting solar energy, etc. And I think that's where we need to go, in the future, because we, like I said, petroleum resources are finite. In fact, they say that, this is coal, petroleum, and natural gas, they will not be there after another 300 years or so. Okay. Coal, actually, the scientists have predicted that it will be exhausted in another 300 years. The petroleum will be exhausted in another 100 years. The natural gas will be exhausted in another 200 years. Okay. So all these, modern developments will go down the drain, if we don't have the resources for chemicals. So that's the important message I just wanted to convey. Next slide, please. Now you can see here, I will not get into all these details, but all, like I already mentioned, these 70,000 plus chemicals can be derived from those 7, basic building blocks. And petroleum industry is actually refinery is considered as a mature industry. Okay, all the processes have been highly optimized, like isomerization, all those kind of alkylation reactions, and these are very cost effective. In fact, petroleum is considered to be very cheap, and that's why we in fact don't have respect for, like, say, plastic bags. We just litter it or we just throw it because it's very inexpensive, because the petroleum is a cheap source at this stage. Of course, the prices have been increasing, and a lot of infrastructure has been built around this petrochemical industry, and there has been investment of hundreds of billions of dollars, in the petroleum industry. And the fuels are also made from these basic building blocks. Okay, so processes used today to make petrochemicals are shown in this slide. Next slide, please. But of course, just go back. Like I was telling, we have consumed these petrochemical resources. Okay, and the rate of consumption has increased, over the last 60 years or so. Okay, in fact, humans have consumed more petroleum resources in the last 60 years than what they have consumed when the man emerged on this earth. Okay, so at the rate at which the petroleum resources are being consumed, so that is really worrisome. And then another point is, the waste which is generated, like we talked about carbon dioxide, which is a wasteful reaction, or waste generation. So likewise, this what I have shown here is a example of what happens to the when the intended use of a polymer is over or done. These are actually discarded in the environment, and we see this kind of scenes, which becomes an eyesore actually. So the plastic, which is actually very wonderful material, because we cannot imagine the modern world without the plastics, but they have actually come under scrutiny. A lot of blame has been given to our plastics are associated with degradation of the environment. Okay, so one of the very important property of plastics is the durability. Okay, for that actually they score advantages over other materials like glass, metals, etc., wood, etc., because they are durable. Okay, and plastic industry is actually 300 million tons industry. We produce actually 300 million tons of plastic every year, but only hardly 10% of that gets recycled. Okay. Now imagine this industry is also growing at a rate of 10% per annum. So if we keep on producing plastics, of course we need resources like petroleum resources to produce these plastics, and then also if we are dumping it in the environment, okay, then imagine the earth space is limited, so there will be no place for us to live. If we keep on producing plastics at such a huge rate and also discarding it into the environment. So these are the two major issues which we are confronted with. Like, how do we conserve these resources and how do we minimize the waste? So these are the two important questions the chemists are asking themselves. Okay, so how can you make chemistry sustainable or chemistry environmentally friendly? So these are the two important topics, I think, which we need to worry about. Now, of course, this picture, I think it's now common knowledge that the Earth's temperature is rising because of the generation of carbon dioxide. Because when these organic chemicals are actually burned or incinerated, they end up into carbon dioxide. This is a wasteful reaction because of burning of fossil fuels and deforestation. It results into carbon dioxide, and the consequences. Okay, you can see the climate change performance index. This is the picture of the Earth, and you can see most of the it's in the category of worst. Okay, the climate change has really taken a toll, and you can see the consequences of that. Okay, and in fact they say that climate change caused by human activity is no longer a distant threat. It is here and now. So it's urgently we should take some action on this. Okay, and Earth temperature has risen by 1.16 degrees centigrade compared to the 19th century. In fact, if the temperature rises to 29 degrees centigrade, okay, we all live comfortably at a temperature of 28 degrees centigrade. But 1 degree centigrade rise in the temperature, in fact, it's going to be really catastrophic. Okay, so we should not allow the carbon dioxide emission or the greenhouse gases. These are basically the causes for the increase in the temperature or global warming. So I think This is also already a textbook knowledge, so I will not dwell too much on the this particular topic. But it's important that we should bring down the emission of carbon dioxide. I think that's the important message. Next slide, please. Now, what are the activities by which carbon dioxide actually gets liberated or generated? So you can see the kind of vehicles which we use. Like I said, we live in an energy-driven world, and all these cars run on the petrol or diesel. Okay, and there's an oxidation reaction, which happens. These hydrocarbons get converted into carbon dioxide, and when we actually also make chemicals in the factories, there is a lot of carbon dioxide emission. So each year, 36 million tons of carbon dioxide is emitted globally. So these are all numbers which really are worrisome. Okay, and as you can see, the carbon dioxide level, which is shown in this graph here, for centuries, atmospheric carbon dioxide had never been above this line, which is shown here, because the science and technology actually, like I said, in the last 50 or 60 years, we have consumed more petroleum or more diesel or all those petroleum resources. That's why there is a sudden rise in the carbon dioxide level in the atmosphere. Okay, next. So that brings us to the topic that all these activities which we have done so far, we meaning the human have done on this earth are not sustainable because of, and mainly two reasons: the consumption of the resources, which are very precious and very limited, okay, and the emission of carbon dioxide. Okay, so that brings us to the topic of sustainability. Okay, so sustainability is actually defined as the ability of the human beings to meet their own needs without compromising the ability of the future generation to meet their needs. So what this means, we should leave these resources for the future generations. Okay? Like I said, there's only one planet in this universe, that is the Earth, where the life can exist. Okay, so if we destroy this planet or the environment, by our acts, I think future generations are not going to excuse us. Or okay, so we need to be, always keep in mind the environmental, sustainability. So that's why whatever chemistry we do, whatever manufacturing of chemicals we do, it should be done in an environmentally friendly manner and keeping the concept of sustainability. Of course, this needs a separate lecture, if I were to introduce the concept of sustainability. But what is important is, we should not pollute the environment, and we should actually conserve the resources or use the resources which are renewable, meaning, which are available to us again and again, annually. And that's why the agricultural waste product comes into picture. Okay, next. Now this is an important slide, and I just would like to spend some time talking to you about this, particular slide. Why we should go to biomass, which is an, of course, like I said, we are making food from agriculture industry, but there are also, waste products which are generated in the agro processing industry, and those how can be utilized to make the chemicals. Now, what we do in chemical industry, like I was telling, these are the three primary sources: petroleum, natural gas, and coal. Okay, and in chemical industry, what we do, we carry out some transformations, on these hydrocarbon sources, and convert them into fuels, chemicals, and polymers. And I already told you, like, the chemicals industry share is 10% of the petroleum resources are used by this chemical industry. Okay, now we some many times we don't give, we don't appreciate, or we don't think about it. So what happens, when these polymers or chemicals or fuels are used for the intended purposes, within 1 to 10 years, they actually get converted into carbon dioxide. Because when the plastic is burnt, it gets converted into carbon dioxide. In the vehicular emission also, it is carbon dioxide. Now see, and the petroleum formation, it actually takes more than 10⁶ years. Okay, and as you know, these fossil resources have formed from biomass and agricultural crops, through all geothermal reactions under very high pressure at high temperature. This biomass, they are all converted into petroleum, natural gas, and coal, and this actually takes more than 10⁶ years. Okay, compare the time scales now. These are the chemicals which required 10 days to 6 years to form, and we human beings take these resources and convert them into carbon dioxide within 1 to 10 years. Okay, so that's why it is called as unsustainable, proposition. Okay, and these sources are limited. Now see what plants do. In fact, that's why important reaction I was telling, converting carbon dioxide back into the hydrocarbons or carbohydrates. And what the poor plants do, they take carbon dioxide and by wonderful reaction which is called as photosynthesis, they fix carbon dioxide. Okay? And this actually happens annually. Carbon dioxide is converted into carbohydrates. That's why these are renewable resources. Like these are produced annually, as against the petroleum resources which take more than 10 days to 6 years. Now the question is, if these fossil resources are not available to us, where do we get all these chemicals from? And that's where this biomass or agricultural waste product comes into picture. Okay. And that's where Professor Ananda Halgari's talk was very important, because he talked about catalytic transformations, or biochemical transformations by which we can convert this biomass into chemicals, fuels, and polymers. Okay, so this is the next big thing. Okay, in the chemical industry, because biomass is annually produced, and we can use catalytic reactions. Okay, biochemical reactions which are environmentally friendly or green, concepts. Again, I will not have time to introduce all those concepts, but one of the there are 12 principles of green chemistry given by Professor Paul Anastas. I will not get into those details, but the 7th principle of green chemistry is to make use of renewable resources as the source of chemical. Okay, so this is in line with or in tune with the principles of green chemistry. Using catalytic transformation, how can we convert biomass into polymers, chemicals, and fuels? And when I say biomass, means it's we are not competing with the food. Okay, the food is available, and also the waste products which are available in agro processing industry can be converted into these chemical. Okay, so this is actually sustainable proposition for the chemical industry. Okay, to utilize biomass rather than using fossil resources. Now the question is, when we talk about renewable chemicals, is it new? It's not new actually. Okay, if you go back in the history, you'll find that man always depended on the nature. Okay, for the food and for other applications also. Okay, so you can see here, the oil industry has actually picked up, the petroleum industry only in the last 50 to 60 years. And the world depended on bio-based processes to produce many chemicals. And Mother Nature is a great scientist. As you know that in the nature there are so many chemicals which are produced. In fact, there are so many drugs, so many pharmaceuticals, in fact, so many polymers which are produced in the nature. And Mother Nature produces, in such a fantastic manner. There is absolutely no pollution. Okay, because the recycling mechanisms are in place. Okay, if you talk about wood, the proteins, they are all polymeric materials which are produced in the by Mother Nature. Okay, but this industry, which is actually huge compared to the modern chemical industry, but there is absolutely no pollution. Okay, so we have to go back and mimic Mother Nature. Taking those resources, how can we produce chemicals, fuels and polymers? I think that's what chemists are trying to do now. Next. Now, of course, these are some of the motivation or why we should go for renewable chemicals, because this is driven by society and technology. Because what we are talking about is now responsible care. Okay, whatever we do should be actually done in a responsible manner. So these are the kind of mega trends which are actually reshaping the chemical industry. Okay, and of course people are also become aware of these environmentally friendly products. So people want to buy. In fact, they are willing to pay a little higher price, but want to go for products which are made which are eco-friendly, or there is an eco label. Again, this is a huge topic, so I will not get into those details. But there is a shift from chemicals which are harmful to the environment to the chemicals, and that's why you see that people are going for organic farming, all those things. Of course, these are points of debate and discussion, but basically people are going for renewable chemicals, and that's why it has become very, very important in the current times. As I already mentioned, this bio-based chemicals or bio-based polymers is not a new concept at all. Okay, in fact, as back as 1897, a German chemist, he made this plastic which is used for making buttons from the proteins which are derived from milk. Okay, then celluloid, as you know, cellulose is and the lignin. These are the most widely available products of in the mother nature. Okay, and chemists have converted that into celluloid by some chemical transformation, and then mixing camphor sulfonic acid with cellulose. This Alexander Parks, he made a product which is called as Parkesine in 1862. So as you can see that throughout the history we have made the humans have made products based on agricultural waste products. Okay, and in fact the first synthetic polymer was made by Leo Baekeland in 1907. By reacting two simple chemicals like phenol and formaldehyde. So the synthetic polymer industry has a history of only hardly 110 years. Okay, in fact, last year we celebrated 100 years of concept of macromolecules. 1920 this concept was proposed. In fact, even this before this concept was proposed, synthetic polymers were made. Okay, but as you can see here, throughout the history, man has depended on the polymers which are derived from nature, like cellulose, lignin, then in fact polylactic acid, what is much talked about, biocompostable polymer, was produced back in 1920s. Then polyhydroxy alkanoids like polyhydroxybutyrate was produced in 1926, and as long as 1930, soybean-based bioplastic car was introduced by Henry Ford. And as you know, the Ford car, this name is associated with cars. Okay, so you can see that a lot of bio-based products have been made, and actually they are coming to prominence now. Next. Now the question is, what are those drivers for renewable raw materials? It is much more than just to have nice to have for sustainable polymers. Like these are the three important aspects when we talk about renewable resource-based chemicals. That is resource availability, and as I mentioned, these are available in huge quantities. Okay, cellulose, lignin, etc. And we have to worry about the environment. And of course, the product has to also perform. And in fact, I'm going to show you. In fact, sometimes the products which are based on natural resources do much better, in terms of efficiency and efficacy. Okay, so improved performance with newly available raw materials and product differentiation. And what is more important from environmental standpoint is the renewable material percent, carbon footprint, and we call about life cycle assessment. Again, these are the new terms probably for the students, but these have become very, very important. Okay, we should not cause any harm to the environment, and there are of course regulations which are strict. In earlier days, up the chimney and down the river, that was the norm in chemical industry. They didn't care so much about the environmental pollution or the degradation of the environment, but the regulations have become very strict. Okay, and the certifications also, you just cannot introduce a new product into the market, especially in the developed countries, unless it is certified. Okay, and also there's a question of image of the companies. If a company introduces a product which is not environmentally friendly, they may lose the business. So these are the kind of regulations which are coming into picture. And there are, of course, as you know, so many laws and regulations which have been made, like Paris Convention, and all those things. Okay, and of course, another is the scarcity of fossil resources. I already elaborated on that. So we cannot depend indefinitely on these fossil resources. Okay, next. Now, as you can see here, the number of publications on bio-based polymers are increasing, and this has really, picked up in the last 30 years or so. This graph just shows, the number of publications from Web of Science on bio-based polymers. Okay. Of course, this is not a new. Like I said, Mother Nature produces a lot of biopolymers, but of course there is certain limitations. These cannot be used for heavy-duty applications. And I'll come to that. Next. Of course, like I said, polymer industry is 300 million tons per year industry. It's growing at the rate of 10%. But if you think, if you assess the status of bio-based polymers, the percent share of bio-based polymers is actually very marginal, at this stage. Okay, but the question is, like all these big names, like BASF, Arkema, or all these big companies are into this market. Okay, and there are many companies have announced that 25% or 50% of their products will be based on bio resources. Okay, next slide. And as you can see, whatever chemicals we produce from petrochemical industry are in principle, possible to obtain from bioresources. As you can see, the best example is natural rubber. All these are, the household names like polymethyl methacrylate, polyethylene terephthalate, PTT. All these chemicals, polymers, in principle, can be derived, from bio-based, chemicals. And I will elaborate on that in the next slides. Of course, these are the few examples of commercial bio-based polymers. So it's no more a laboratory curiosity, but these polymers which are biodegradable, as you know that the polymers derived from petrochemicals like hydrocarbon polymers, basically like polyethylene, polypropylene, etc. They are non-biodegradable. Okay, and what people are looking for is polymers which can be degraded in the environment, so that ultimately they end up into simple chemicals, and they are not don't remain, or they are not persistent in the environment. Okay, and you can see here some of the examples like polylactic acid or polyhydroxyalkanoates, polycaprolactone. These are some of the polymers which have already been commercialized. And in fact, this is a very interesting example, which has been introduced by Avantium, that is polyethylene furan, which is based on furan dicarboxylic acid, and which is in a way superior to polyethylene terephthalate. Okay, which is very commonly used in water bottles or Coca-Cola bottles. So a lot of work is actually happening on developing technologies for polyethylene furan, or in fact the polyethylene, which is the world's largest consumed or produced polymer, that is polyethylene, which is currently made from hydrocarbon sources, can also be made from bio sources. In fact, there's a company called Braskem Industries. They produce polyethylene wherein the ethylene is derived from ethanol, and which comes from molasses. So as you can see, the molasses is a waste product of sugar industry. So it can be converted into ethanol and then converted to ethylene and made into polyethylene. So likewise, you can see there are several examples of, and in principle, like I said, most of the polymers which are made in petrochemical industry can be produced from bio sources, but these are some of the examples of commercial bio-based or biodegradable polymers. Next slide. But as you know that in, like I said, Mother Nature produces a lot of chemicals, like, and basically they are carbohydrates, oils, fats, etc. But most of these chemicals are aliphatic in nature. Okay, that's the important point I just wanted to bring here. And if you look at this, polymer pyramid, you can see polymers can be actually categorized or classified by different, schemes. And one is, of course, commodity polymers, which are high volume, low cost, like polyethylene, polypropylene, polymethyl methacrylate, or polyethylene terephthalate. These are commodity polymers, which are very commonly used. And then next comes the engineering polymers. And the simple definition is, you can apply them for engineering applications, wherein we use like metal, glass, etc. So like polycarbonates, ultra high molecular polyethylene, nylons, these are called as engineering polymers. And then there is a third category, which is low volume, high cost. These are high performance polymers, which, like I said, which are used in heavy duty applications, like under high temperature, or they exhibit high chemical resistance, etc., high mechanical properties. And these are mostly polymers containing aromatic units in the structure, like polyether ketones, polyether sulfones, polyether imides, etc. And these kind of polymers, the commodity polymers are, like I said, a low cost, and the performance goes up, when we talk about high performance polymers. Now, what I've shown in the right hand slide is, the polymers which can be also derived from biosources. So you can see that most of the commodity polymers can be produced from biosources. Also, engineering polymers, there are now building blocks or monomers which are available for producing engineering polymers, and these building blocks come from renewable resources. But what is missing, or what is the gap, is the high performance polymers. They are still only in the laboratory scale. There are of course a lot of reports, like I showed you in the bio-based polymers. The number of publications are going up. So this is an area which needs further attention or further research. And the world, like I said, needs commodity polymers, and the world also needs high performance polymers, especially in space applications, high temperature applications. We need high performance polymers which are based on aromatic sources. Okay. And I'd like to bring your attention, draw your attention here. Most majority of the commercial bio-based polymers are aliphatic in nature, and bio-based aromatic polymers are still at a laboratory scale. So this was one of the gaps in the literature or on the commercial scale. Okay. Like I said, the Mother Nature is a great scientist, and there are so many products which are available, and they are unique. Okay. Again, this needs a lot of discussion, but I will just flash here what are the sources available for deriving bio-based chemicals. And you can see here the plant residues like non-edible oils, hemicellulose, then animal residues like chitin and chitosan, proteins, algae oil, like polysaccharides, bacterial biomass, then wood like cellulose, lignin. You can see the numbers, world produces like 108 million metric tons per year of cellulose, 100 million metric tons per year of lignin. Okay, compared to like 300 million per year plastic what we produce. You can see natural rubber, tannins, roseins, terpenes. So these are the plentiful resources which are available to us. The question is, how can we be creative and imaginative and make use of these waste products and convert them into resources? And by the way, Mother Nature is so generous. I tell you what, only 5% of these resources actually humans use annually. These are the renewable resources produced annually, and they say that as long as sun is there, the renewable resources will be there. So these resources are guaranteed. Okay, of course it has to rain, meaning we should protect our environment. So if it rains and as long as sun is there, these resources will be available to us. And they are available in plenty. And again, we are not competing with the food here. What we are talking about is the agricultural waste products. Okay, like for example, lignin and cellulose pulp. These are available, as a waste products. So with this introduction, so I hope I was able to convince you that there is an urgent need to move away from petrochemical industry. Basically meaning petrochemical resources, and make use of agricultural waste product as the source of chemical, and convert these agricultural waste products in an environmentally friendly manner into chemicals products, of commercial interest or commercial relevance. And what I also mentioned is, most of these commercial polymers which are being produced currently based on biosources are aliphatic in nature. But there are certain applications where we need aromatic polymers. Okay. Now, talking about the aromatic resources, there are only two sources, major resources. The one is the lignin, which is very complex molecule. Of course, basically it is a polymer. It contains many aromatic rings. I will not get into all those details, and of course I'm going to show you some of the work which we have done on lignin utilization. But the other one is the cashew nut shell liquid. Okay, I'm sure all of you are familiar with this tree or the fruit here. I will not get into the further details. Of course, this was India is the third largest producer of cashew nut shell liquid. It's a non-edible oil, like castor oil. India is the largest producer of castor oil. Okay, and it's basically a long hydrocarbon chain, chemicals. They are aliphatic in nature. But cashew nut shell liquid, it's a nature's gift to mankind. It's a aromatic phenol. Again, I will not get into all those details. It's a non-edible. So alternative market is not only desirable but essential. And this cashew nut, is a king of dry fruits. Okay, and it's the crop of the poor man and food of the rich man. Okay, like countries like USA, etc., we export cashews to those countries, and this plant actually was brought to India by Portuguese, to for the soil conservation, and this plant is grown in several states like Andhra Pradesh, Karnataka, Orissa, and Maharashtra. And this is a big industry, in fact, a lot of people are employed in cashew processing industry. Like I said, it's a king of dry fruits. But when we process cashew, there is an oil which is, formed, phenolic antioxidant, and Mother Nature actually produces this oil to preserve the, cashew fruit from bacterial attack. Okay, and as you know, most of the phenolic compounds, in fact, we use them as disinfectants, for toilet cleaning, etc. Phenols are used, in dilute, in very low concentration. They are disinfectants. So likewise, to protect this cashew fruit, the nature produces oil, which is a phenolic acid. And as you can see, the chemical structures are shown here. And in fact, this oil contains 16 chemicals. I will not get into all those details, but basically what we have to remember is it's a basically phenolic compound, okay, and with a hydrocarbon chain at the meta position of the hydroxyl groups. And the irony of the situation is, like, though India is the third largest producer, we export this raw cashew nut shell to other countries, developed countries. And there are companies like Carbonet Corporation, Novacard, Palmer International. They process this cashew nut shell oil and convert that into some high value chemicals. Like you can see on the right hand side, the products, epoxy resins which are used in aeroplane, or polyamides or polycarbonates. Those are the kind of products which can be made from products based on cashew nut shell liquid. Of course, I will not get into these details, but one can use these various processes like mechanical extraction, thermal extraction, solvent extraction, pyrolysis method to get this oil. In fact, there are videos available. If you Google, you'll find the various techniques which are available for extraction of cashew nut. But the mechanical and thermal extractions are favorable and are commercially practiced. And you can see that here, cashew nut shell liquid, of course, the structure of this molecule, was established back in 1847. You can see it contains basically cardanol, cardol, 2-methyl cardol, anacardic acid, and some polymeric acid. Okay. Next. This is, of course, the production. Like I already mentioned about West Bengal, Jharkhand, Kerala. These are the states: Karnataka, Andhra Pradesh, and the other countries like Brazil, another country, Vietnam. Basically, the African countries. Yeah, next. So I already mentioned to you, like, there are companies in the United States. There is a company in Poland, Vietnam, and China who are actually processing cashew. And cashew plantation actually, happens in countries like Vietnam, Africa, India, and Brazil. Next. Now, this is a slide which I just want to emphasize, especially to the students. As you can, like I mentioned, cashew is India specific, meaning it's a byproduct of agricultural industry, cashew processing industry, and for obvious reasons, of course, Indians should work on this. The students should take up this as a project, because this is India specific, and you can do value addition or valorization of cashew nut shell liquid and convert them into chemicals which are environmentally friendly. And obviously, you can see that here several laboratories like the National Chemical Laboratory, Institute of Chemical Technology, Mumbai, or other CSR labs or defense labs, ICERs, they are all engaged in value addition of cashew nut shell liquid. And of course, there's a lot of interest. As you can see, the number of publications on this cashew nut shell liquid has exceeded 3,000, more than 2,000 patents and 30,000 citations. And these are the two pioneering researchers. My own guru, Dr. N.D. Ghadge, who was the head of the polymer division at NCL, and Dr. C.K. Pillai from Kerala. These two gentlemen have made immense contribution to valorization of cashew nut shell liquid. Okay, next. These are some of the Indian companies. So what I want to emphasize here is there's a lot of demand for valorization of cashew nut shell liquid. So this is a something a topic which needs to be worked on. Because in fact, many times what happens, students choose a problem for their research or for PhD, which can be solved. But I think this is a topic which needs to be solved. This is the kind of project which needs to be worked on. Okay, next. But there is a lot of scope, and this is again in tune with Atmanirbhar Bharat, wherein we develop our own technologies, and export to the world rather than exporting the raw cashew nut shell oil. Next. And another, important aspect of here, this being bio-derived. In fact, this is rated, green. You can see here, phenolic compounds, which are made in petrochemical industry, are considered as substances of very high, this rating is, you can see red, but cashew nut shell liquid is given green tag. So all these other substances are of very high concern. Okay, and sooner or later, these chemicals will be banned. And I'm sure most of you know that bisphenol A has come under scrutiny. Okay, and which is actually a darling monomer of polymer chemists, because a lot of polymers are developed based on bisphenol A. But there are some issues like bisphenol A is been found as endocrine disruptor. So there are health issues associated with all these phenolic compounds, which are widely used in surfactants in polymers. So that's why there is a lot of scope for utilization of cardanol, because it is safe to use, safe to handle. Okay, next. Now this is something I just want to draw your attention to. And from a chemist perspective, of course, like I said, cashew nut shell oil contains 16 chemicals. Okay, 16 chemicals, but it can be refined and distilled and etc. And then you get cardanol, which is basically a alkynyl phenol. So you can see here what I have shown in the arrow is the reactive sites which are present in cardanol. Okay. So there is a phenolic hydroxyl groups, and this, of course, a textbook knowledge. One can take advantage of the phenolic hydroxyl group and carry out reactions like acylation, dehydration, phosphorylation, pulmonitherification, etc. Okay, on the phenolic hydroxyl group. Now there is a double bonds which are present in the side chain, and I'm sure the students who have studied chemistry at undergraduate level or in the junior college will know that what are the different reactions of double bond, like hydrogenation, bromine addition, epoxidation, hydrosylation, hydroboration, phenolation, ozonolysis, metathesis, and recently introduced click reaction, like thiolene reaction. So these are the various possibilities which one can carry out reactions on the double bonds in the side chain. And also this aromatic ring being electron rich, one can carry out because of the electron donating effect of this OH group. The ortho and para positions are electron rich, so one can carry out aromatic electrophilic substitution reactions like halogenation, nitration, sulfonation, or condensation reactions, or coupling, or ring hydrogenation. Okay, and more importantly, this is what only one molecule which at least I know of, which is so versatile, which can undergo so many reactions and doesn't need much functionalization. You can preserve all the functional groups which are gifted by the nature, like OH group, aliphatic side chain, the aromatic ring, etc., and make products which are differentiated. These are not yet another products, but the products which have got some enhanced performance. So that is something unique about this cardanol. And more importantly, these building blocks or the polymers which are made from cardanol are carbon neutral. Okay, that's something important. Like when you take petroleum resources, actually we are converting that into carbon dioxide, but here these are carbon neutral monomers. Okay, I think that's something very, very important, and that's why these are sustainable building blocks. Okay, next. Of course, like I said, there are industries around the world which make products. Like this can be a substitute for phenol, which is derived from petrochemical industry. And as you know, the phenol formaldehyde resin. I talked about Beckland discovery of phenol formaldehyde resin. So one can substitute phenol with cardanol and make phenol formaldehyde resin. And as you know, they are widely used. In fact, these materials are more than 100 years old, but there are more than 1,000 applications of phenol formaldehyde resin. As you can see in composites, electrical insulation, laminates. These phenol formaldehyde resin kind applications. So one can make the same, of course, polymers with improved properties in certain way, using cardanol as the substitute for petrochemical based phenol. Then one can make epoxy resins. I'm sure all of you know what are the epoxy resins, which are used in adhesives, building and construction industries, in electronic industry, transportation, etc. The same, like instead of bisphenol A, one can use this cardamol and make various epoxy reagents, and then epoxy curing agents like amine, etc. So you can see there are a lot of applications and industry is making. Now let me come to our own contributions to valorization of cashew nut shell liquid. So as a chemist, what we embark on journey to make use of this cashew nut shell liquid to derive some useful building blocks, making use of some simple organic transformations. And I'm going to show you, whatever reactions we have used for a transformation of cashew nut shell liquid are basically textbook organic reactions. Okay, and of course this is just not only laboratory curiosity, but these monomer synthesis or polymer synthesis were demonstrated on kilogram scale. So what I meant is, these are all scalable processes. Okay, and then we have targeted for some high-end and specialty application, and then created intellectual property, meaning some patents for CSIR. And then we also have transferred certain technologies to industry and created skilled human resources to address renewability challenge. Okay, so that's what I'm trying to do in this lecture. The students should be aware of the consequences of what they do. Maybe like I said, we do something with good intention, but there should not be any relatable consequences of those. So one needs to teach to the students, how we can make the chemistry sustainable. And this is, I think, something which we have been able to do successfully, to imbibe on these students that how one can do chemistry which is sustainable. Okay, and as we have developed certain products, there have been job potential for job creation in India. Okay, and these are some students, and I who worked on these projects on utilization of cashew nut shell liquid. Okay, so instead of giving the literature review, I'm going to concentrate only on few examples and tell you how one can do valorization of cashew nut shell liquid using those simple principles like simple organic transformations. This is a busy slide, but what I want to tell you, in fact, all these reactions can be even performed in an undergraduate laboratory. You don't have to do this. We don't need a fancy laboratory like National Chemical Laboratory to do all these kind of transformation. But what you need is, of course, the creativity and imagination. Okay, and as you can see here, very simple reactions. I just want to describe this synthesis of diamine and bisphenol. We take this cardamol, reduce the side chain double bonds to make 3-pentadicyl phenol. Okay, and the green color shows that these are all carbon coming from bio sources. So these are carbon neutral monomers. You can see of course these are partially bio based monomers. Then this aromatic ring can be reduced to cyclohexanol, then oxidized to cyclohexanone. So this actually is an equivalent to a ketone. So one can condense with phenol and you get bisphenol, and condense with amine to get diamine. So you can see here the reactions involved are hydrogenation, oxidation, and condensation. Very simple reactions, amenable for scale up, but you get some interesting monomers. Okay, in fact, these kind of monomers cannot be achieved from petrochemical resources, because as you know, it's very difficult to put a alkyl chain at the meta position of phenol, because being an electron rich ortho and para position, the alkylation will happen only at the ortho and para position. But like I said, Mother Nature by biogenesis routes, it makes this interesting molecule. And then the next question is also why C15 chain? It's odd carbon chain. Okay, and as you know, in terpenes you have this 5 carbon, like isoprene. So there's something called as isoprene rule. So you have chain like C15 chain here. That is at meta position. So you get these interesting bisphenols. Okay. And then you can see here, very simple chemistry. We have exploited Ullmann esterification with bromobenzene to make this diphenyl ether. Then bromination, cyanation, hydrolysis, esterification, hydrazide formation, aldehyde formation, etc. So you can see whatever monomers the polymer chemist needs for synthesis of basically step growth polymers or condensation polymers can be made from these chemicals. Okay. And of course, they have some added structural features like pendant C15 chain, built-in ether linkage, etc. I will not get into all those details, but you can see, the power of creativity and imagination to design and synthesize new basic building blocks for polymers. Next. This is again a demonstration, like you can do a lot of interesting chemistry on this molecule and make a range of monomers. For the want of time, I will just skip this and take you to the next slide. And as you can see here, 6 of my PhD students have worked on this topic, and you can ask for any monomer, what a polymer industry needs or a polymer chemist needs to make a step growth or condensation polymer. We have made it in the laboratory. Okay, you can see here bisphenols, diamines, diacids, diisocyanates. So a range of validated chemicals and difunctional monomers were synthesized. Of course, it's a lot of hard work. Though I'm trying making it simple, maybe I'm probably oversimplifying it. But of course, this needs a lot of skills to convert this agricultural waste product, which is quite impure to begin with. But when you talk about synthesizing step growth polymers, you need monomers which are close to 100% pure. Okay, then only you can build a high molecular polymers. So these students were able to make these monomers in kilogram scale in quite pure form, and you can see that a range of monomers have been prepared. Starting from a single chemical. So this kind of versatility you will not get with any other natural product. So that's the beauty of, and that's the uniqueness of cashew nut shell liquid. Of course, this is a lot of hard work of 6 of these students who have produced a lot of these monomers. And, in the next slide, you can see not only synthesize the monomers, but we have also made use of these monomers to solve some of the problems, with these aromatic step growth polymers. What I have shown here, some of the, I think, if the students are from organic chemistry background, probably I will not spend much time talking about that. But we have made use of this. Next slide, please. We have made use of these monomers and prepared, polymers which are of high molecular weight. Studied some structure, property relationship. Next. Then we have made polyamides, which are organic solvent soluble, which can be cast into films. And you can see the thermoplastics. All these aromatic high performance or engineering plastics we have made, like aromatic polyesters, polycarbonates, polyamide imides. And what we basically focused on is improving the processability of these otherwise rigid polymers. Okay. Next. And then not only thermoplastics, but we also have made thermosettings like epoxy resins, cyanate esters, propyl resins, etc. And then we also have used this, dibromo precursor to make the first example of hydrocarbon solvent soluble dilithium initiator, which is used required to make styrene, butadiene, styrene thermoplastic, copolymers. That was also possible with this precursor coming from cashew nut shell liquid. Next. So, to summarize our own contributions to utilization of cashew nut shell liquid or cardinol, now we have published more than 25 research papers, filed 10 patents, published 1 review article, and we also are invited to write a book chapter, and 7 PhD theses have come out of this. We completed some 5 industry projects. And to just capture all of that, what we achieved by making these monomers, we have prepared polymers which are soluble in common organic solvents, low moisture uptake because of the C15 chain, hydrocarbon chain, improvement in ductility, and then modulation of glass transition temperature, of course at the expense of crystallinity, thermomechanical properties, and chemical resistance. So what we propose and what is our contribution to the world of step growth monomers based on bioresources is all these monomers which are recommended as co-monomers to tune the properties of high performance polymers. So this is of course futuristic. So when the world will run out of these petrochemical resources, we have all this technology or all these products ready, which can be derived from agricultural waste products, okay, like cashew nut shell oil. And we can make all those polymers which are needed for the heavy duty applications. So that's what our contribution to this area of sustainable monomers and sustainable polymers. Of course, these are you can see a range of applications of cashew nut shell products in epoxy industry, epoxies like in foundry industry, paints, coatings, adhesives, varnish, then surfactants, polyurethane industry, plasticizer, rubber additives, anti-static agents. So you can see, this material is so versatile, cashew nut shell liquid. You can make a range of products, okay? And that's where I think we have made our mark, utilize cashew nut shell oil and derive these products. And again, like I said, this is an India-specific project because we produce cashew nut shell oil. We're the 3rd largest producer, okay? That's what I think. That's why what I want to drive. What message I want to drive home is to work on the problems which are of relevance and which need to be worked on. So that's the message I just wanted to convey. And Ramesh, if time permits, I would like to talk about valorization of lignin. Otherwise, I will just stop here.
Yeah, please carry on for another 10 minutes. No problem.
Okay. Sorry, I'm rushing through, but I hope I am able to convey the excitement to the students.
Yes, sir, your talk is very exciting.
Oh, great. Thank you, Ramesh. So I hope I was able to convey the excitement to students. Like you can choose raw materials which are available around us. And there is no dearth of these kind of waste products. There are so many. Like I said, castor oil. We are the largest producer of castor oil. So a lot of chemicals can be derived from castor oil. Then there are so many terpenes. Basically are available. And what we need is a knowledge of organic chemistry, simple organic transformations, which are actually taught in undergraduate colleges or in postgraduate colleges, universities. Sorry, and make use of that those transformations. But of course, what you need to know is the design principles. So what kind of monomers are desired by polymer industry, or what kind of other products. And as I showed you, starting from a single chemical. Okay. And this is the the power of chemistry, that we can make new chemicals. As you know, like in the periodic table there are only certain number of elements, okay, like I said, but synthetic chemists have produced 88 million compounds. Okay, this is again possible because of the knowledge of organic transformation or chemical transformation, bond forming reactions, bond breaking reactions, rearrangement reactions. That's how chemists, and in fact, again, this is something I want to tell to the student, that every day in this world, 15,000 new chemicals are produced, across the globe. Like all the researchers who are engaged in, the PhD program, they produce new, chemicals, new materials. Okay, and this number is actually increasing, as the focus on research is increasing. So there is a lot of tremendous scope. There is no looking back. In fact, this number is going to go increase, I tell you. Okay. So again, I'm sure this is not the end of the story. One can definitely come up with again some new derivatives, new molecules based on cashew nut shell liquid. So the story doesn't end here, or doesn't stop here. Okay. So they say it is an enabling science. So you can keep contributing, and I'm sure those bright young students definitely will have some new ideas and contribute to the valorization of all these agricultural waste products. I'm not selling only CNSL. The CNSL we just chose because India is specific, but there are so many other agricultural waste products which are available and which can be put to use or made use of. Okay. The next, coming to this lignin, which is a byproduct of paper and pulp industry, and again see the numbers. 100 million metric tons per year of lignin is obtained from paper and pulp industries. Again, for the want of time, I will not get into those details, but it's basically a polymer made up of so many aromatic segments, and these are the chemicals which can be derived by degradation of lignin. If you break those bonds, you get those kind of chemicals. And what I have shown in the red circle, these are the molecules which are of our interest. And another interesting aspect about these molecules is, they contain functional groups like hydroxy, carboxy, or aldehyde. And these are the functional groups which are required for polymer synthesis, because one can exploit the reactivity of these. And as again I mentioned earlier, what was missing in the literature is the aromatic basic building blocks for polymers derived from biosources. So our aim was to exploit these lignin-based aromatics for expanding the operative temperature range of green polymers. With this objective motivation, or with this objective, we embarked on journey of utilization of lignin-derived aromatic chemicals. Again, this is a busy slide, but I just want to tell you a glimpse of it. I just want to give a glimpse of it. What is all possible? Okay. Now you can see on the left-hand corner here, we have a student of mine, Dr. Sachin Kuire. He reacted these two simple chemicals, furfural and guaiacol, which is available from lignin. Furfural is also available from biosources. Okay. And as you can see, he was successful in synthesizing the first example of a fully bio-based bisphenol. You can see it's completely green color. All the carbon atoms are derived from biosources. I already told you, like, world is looking for an alternative to bisphenol A. Bisphenol A is a very important, monomer for polymer synthesis. But in fact, there are so many regulatory issues, health and safety issues are there associated with bisphenol A. So we have actually now positioned this bisphenol as an alternative to bisphenol A, which is made from acetone and phenol condensation. Now you can see here these two simple chemicals, perfluoride and guaiacol or syringol, reacted in a one-step synthesis by simple condensation reaction at 100 degrees centigrade. We were able to make this bisphenol. And on the next, you can see a diacid or diisocyanate. So were made. You can what is to be noted here, most of the carbon atoms, I mean, all of the carbon atoms come from renewable resources. We can see again a range of chemicals were produced from lignin derived aromatics. And this is another example, like we have made isocyanates, which are important monomers for polyurethane industry. So Sachin, in his PhD thesis, he was able to produce some 23 new monomers, starting from lignin derived aromatic chemicals. Okay. Unlike in cashew nut shell oil, at least those were partially bio-based, but here you can see these are mostly bio-based, except these heteroatoms like nitrogen, they are not bio-based, but otherwise the rest of the carbon atoms are coming from biosources. And he was able to produce all these high performance or engineering plastics like polycarbonate, and then he has generated a lot of basic data on synthesis, characterization, structure property relationship. And more importantly, it's not a simple bisphenol, but bisphenol with a pendant furyl group, which is capable of undergoing click reaction, and this has come into quite prominence because you can convert this thermoplastic into thermosetting, which is a thermally reversible kind of reactions, meaning you can increase the mechanical properties, etc., of this thermoplastic and then recycle it, simply by heating at 130 or 140 degrees centigrade, where this retro Diels-Alder reaction takes place. So this is what has been vividly demonstrated by making so many type of polymers like polycarbonate, polyether ketones, polyether sulfones. Again, for the want of time, I will not just get into all those details, but you can see here, we not only bio-based polymers, but polymers with some special structural features, or how can improvise it, or how we can recycle, these are kind of polymers. Or this is an example of a polyurethanes derived from isocyanates. Or you can see here again a bisphenol with a pendant clickable groups like azide and malimide, etc., starting from liuronic acid. So again, you can see from lignin derived aromatics, we were successful in synthesizing a range of high performance polymers like polycarbonates, polysulfones, polyether ketones, polyesters, etc. And then again, what do we achieve, by making these polymers? Again, solubility in common solvents, opportunities for functionalization, thermoreversible cross-linking, all those are the, again, we recommend these as co-monomers to tune the properties of high-performance polymers. Next. So that brings me to the concluding slide. So I just want to summarize by saying that, we have made a clever use of cashew nut shell liquid and lignin derived aromatics, which are actually bio-privileged molecules. Okay. And we have made monomers which are differentiated, meaning they are not just yet another monomers, but monomers with some special structural features. Okay, and that gives them some advantage in terms of the performance. So that's why we call them as performance advantage monomers, possessing some special structural features. And we just didn't stop at that, but we made use of these basic building blocks for synthesis of modified thermoplastics and thermoset materials, which are of industrial relevance, like epoxy resins, polycarbonates, polyester, etc. So this is our recommendation that cashew nut shell liquid is a versatile renewable resource material with high potential for commercial exploitation. Okay. Now, as already shown you, there are industries who are looking for these kind of chemicals. We of course demonstrated Diels-Alder malimide click reaction was exploited for thermoreversible cross-linking. So the synthesized bio-based building blocks are drop-in replacements. You don't want to change anything in the production processes, but they are like bisphenols or diamines. That's why they are called as just drop-in replacements and are welcome addition to the family of aromatic step growth polymers, which was actually sorely missing, in the area of bio-based monomers. So this is our contribution to the field of bio-based monomers. Next. So this is something which I again want to drive the message home. So all these years, we have depended on fossil resources. So this is the story of the past now. Now the future is bright, and there are a lot of opportunities to work on bio-based resources as the source of monomer, and that's where the future lies. So there is nothing that biotechnology cannot do. Today there is a renewable alternatives for almost every conventional material and corresponding application. So I am sure if we follow this and if we mimic Mother Nature, I think we will be producing all those chemicals, polymers in an environmentally friendly manner, and the chemical industry will be definitely sustainable. Okay, this is the I think the last message I just wanted to convey, that chemistry of course has to be sustainable. The chemicals have to be sustainable, produced in the environmentally friendly nature. So we have to be with nature and not against the nature. That's the message I just wanted to convey. And with this, I would like to thank all the listeners, all the participants for patient listening. And Ramesh, I would like to thank you for giving me these opportunities. And I'm also grateful to all my students who did all the hard work. It's easy for me to just make a presentation, but they did put in a lot of hours in the laboratory and did this skillful work and made it possible. So this is what I just showed, the art of possible. Okay? So thank you very much.
Thank you very much, sir, for a wonderful talk on sustainable chemical based on byproducts of agro-processing industry. In fact, you spoke on environmental chemistry, green chemistry, and sustainable development, and also renewable energy you touched upon. It was really a wonderful talk. I'm sure students would have got sufficient take-home message to work on green chemistry during their research. With this, I would like to thank you immensely for your time and a wonderful talk. If there are any questions, please, Mr. Umesh.
Yes, sir. There are 3 questions, sir.
Yeah, please.
Sure.
Please.
Sir, first of all, thank you for a wonderful technical session. There is one question from the participant regarding what are the prospects of CCR, sir, carbon capturing system.
Say it again, Umeshji. What is the question?
What are the prospects of CCR, sir?
Carbon capturing
system. Yes, sir.
So that's what I told you. Of course, there is one is carbon dioxide capture and also utilization. Of course, there are already technologies available for capture of carbon dioxide. Like amine, ethanol. There are so many. In fact, this is a separate topic of discussion. But I think what we need, that those technologies are available. But what we need, and as you know, carbon dioxide is a stable molecule. Okay, it has to be activated and then made use of, and convert into various products. And I think Dr. Ananda already showed, one can use carbon dioxide for making carbonates. Okay, and there are so many other, chemicals which can be made. And in fact, there are technologies available now. I mean, of course, it's only at the laboratory stage to convert carbon dioxide back into hydrocarbons. Okay, but like I said, the world has realized now carbon dioxide, you just cannot keep on producing carbon dioxide and pollute our environment. So of course, carbon dioxide has to be utilized as a resource, as a source of basic building blocks, C1 chemistry. There's a lot of effort which is happening. Maybe I can discuss offline with this, particular student. But this is the next big thing, which is going to happen, like utilization of carbon dioxide for deriving chemicals.
Umesh, next question. Mr. Umesh.
Yes, sir. Sorry, sir. There was disconnection. There are 2 more questions, sir.
Yeah, please.
What are some low energy intensive methods that are involved in the capture of CO2, sir?
See, like I said, right now it's the capture of carbon dioxide in aminoethanol solution. Okay, So capture is one thing and then release, so those are the two different aspects. Okay, so carbon dioxide capture technologies are already available. Okay, so carbon dioxide is a Lewis acid. You can capture it in a basic solution, alkali solution, like aminoethanol or ethanol amine, etc.
Thank you, sir. What is the best solvent for EVA polymer, sir?
Ethylene vinyl acetate. EVA is ethylene vinyl acetate polymer. The best solvent is, of course, depends on what application, but I think ethylene vinyl acetate is soluble in solvents like tetrahydrofuran, if I'm not mistaken. Of course, I don't have the right now the data with me, but I think it is soluble in polar solvents like tetrahydrofuran or even chloroform. Again, it depends on the content of vinyl acetate. As you know, polyethylene is not soluble in these simple solvents. Okay, it dissolves only in a solvent like chlorobenzene at high temperature. But ethylene vinyl acetate, depending on the vinyl acetate content, can be dissolved.
Thank you very much, sir.
Thank you.
As of now, we had only 3 questions. Rest we can take offline with the help of feedback form also. That
Sure.
time we will connect you, sir. Over to you,
Okay,
sir.
now, can I request Mr. Dr. Lokesh KS, he is the chairman and professor of Department of Chemistry, who is the co-coordinator of this particular webinar, for his words. Dr. Lokesh, over to you.
Sir, thank you, sir. Are you audible, sir? Am I audible?
Yes, you are audible, please.
Sir, this is one of the most informative talk, because carbon dioxide capturing is an important task in the present industrialization. So the talk will definitely motivate our students, and it will be helpful for the research students and even master students to modify their work as the need of the hour. So thank you very much, sir.
Thank you, Dr. Lokesh. Once again, I would like to thank our esteemed speaker, Dr. Prakash Vadgaonkar, sir, for an excellent talk. I'm sure students will take up research which is of importance for society. Most of sir, whatever explained are of societal relevance. That's why his talk was very interesting. I hope students will pursue their research in that line. With this, I would like to thank you immensely, sir. We'll be
Thank you, sir.
requesting again for talks like this in our future webinars and offline talks. Thank you.
Anytime, Ramiji, anytime. So thank you for remembering me and inviting me to participate.
We always remember you for wonderful talks. Even in Bieber, it was a very exciting talk, sir.
I know. Yeah. I hope we will be able to see each other, in person.
Yeah, sir.
Yeah. Sure. Thank you, Ramiji. Thank you. Bye.
I would like to thank all the participants for being with us for the last 2.5 hours. Tomorrow morning, the session will begin at 11 o'clock. First talk will be by Dr. Shashidhar BS, is the senior scientist at CSIR, National Institute for Interdisciplinary Science, Trivandrum. And the second will be by Dr. Taramani, Assistant Professor, Department of Chemistry, IIT Ropar, Haryana.